Unit 3, Physical Chemistry. This consists of 3 chapters. We're going to start with energetics. When I use the word energetics, what I basically mean is that how in a chemical reaction the energy is involved. Sometimes chemical reactions give out energy, sometimes they take in energy. And when we divide chemical reactions on the basis of thermal energy, we actually divide them into 2 categories. So let's start with the first category first. We call them exothermic reactions. When I use the word therm, it specifically means heat. It means the reaction involves heat in some way. Maybe it's absorbing heat, maybe it's giving out heat. Exothermic reactions are the chemical reactions which give out energy in the form of heat. It's as simple as that. So it's a reaction which gives out heat to the surroundings. So whichever thing you are undergoing the reaction with, you're performing the reaction in, let's take this diagram and as an example. He has taken a small dropper, is putting drop by drops of water in a powder named as calcium oxide. So this entire portion would be the system. I will be using this word quite frequently. The system can be a small bowl, it can be a beaker, it can be an entire cylinder, it can be an entire lab room. The system can be anything which is under consideration, and you are performing your experiment in that specific apparatus. And everything around it, the air around it, this tube around it, this bowl, what it's made up of, the bowl, the air around the bowl, the surface beneath the bowl, every of this part is considered as surroundings. So I am also going to use this word a lot. So as soon as I use this word surroundings and system, you should get an idea what we are talking about. So whatever's under consideration in terms of apparatus is going to be our system, and whatever's around it would be known as surroundings. A reaction that gives out heat to surroundings would be known as exothermic reaction. Now, holding a test tube in which exothermic reaction is occurring, you would notice the test tube gets warmer. An example of exothermic reaction is adding water to calcium oxide, the equation of which is written over here. You're converting a solid substance into another solid substance, but it produces so much heat that you would be amazed to know it's enough to boil water and produce steam, like you can see right in this diagram. Although you're adding liquid water, but that liquid water is being converted into steam right away, which means this is definitely giving out heat more than the boiling point of water, which for pure water is 100 degrees centigrade. So it's producing enough heat to boil all of the water that we are putting in it. Make sense?
I don't understand.
Sorry?
I don't understand.
So simply speaking, it's a reaction which gives out heat. Okay, let me quote some daily life examples. I hope you are familiar with barbecues and bonfires, right?
Yes.
We commonly use coals or pieces of coals for that purpose. And as soon as you bring your hands near that coal, you feel the heat coming out of it, right?
Yes.
That's an exothermic reaction. The reaction is giving out heat. Any reaction which gives out heat is known as exothermic reaction. Burning of coal, burning of literally any fossil fuel like petrol, like gasoline, like kerosene, like natural gas, the gases we commonly use to cook food, stuff like that. Any reaction like that would be considered as exothermic reaction. So exothermic reaction is a reaction which is giving out heat, and you can literally feel that heat. Now, I suppose it makes sense, right?
Yes.
Good, good. So this reaction also gives out heat. We are literally adding drop by drop water. And let me change the color so it's easier for you to see. We're literally adding water on top of the salt. This reaction produces so much heat, and I can write it right over here, that it boils water into steam. That's what he was trying to say, right? So in any exothermic reaction, the products of reaction have less chemical energy than the reactants. Why? Because the chemical energy stored in the bonds of the chemicals is converted into heat energy. This heat energy is released to the surrounding and we can literally feel it. Not just that, the temperature of the reaction mixture uh, and its surrounding goes up. Just like at barbecues, when we burn up coal, and we usually do it at winter nights or winter days, and we enjoy that heat. Since we have very harsh climate, we have very harsh weather on that days, it's the temperature is very low, sitting near to that fire, near to that heat, actually keeps us cozy and warm, right?
Yes.
So we call those reactions exothermic reactions. And the typical sign of exothermic reaction is that the temperature of the surrounding goes up. Okay, so since we are talking about a specific reaction over here, calcium oxide is also known as quicklime. Adding water to it is known as slaking of lime. It produces calcium hydroxide, this stuff, okay, and we call it state lime, right?
Yes.
Okay. Safety note, it is less hazardous to use a lump of calcium oxide rather than powdered. And remember, if you're performing this experiment, add slow drops of water. The experiment is so much exothermic that if you use any extra amount of water, more than drops, it might burn you up. So when you're performing this experiment in lab, try adding small drops of water at a time and then waiting for the reaction and for the steam to appear, and then stay a little bit away from it so that it doesn't burn you. All right. So this safety note is very important while you're performing this exact reaction in lab, which is a very common practice. Let's move on a little quicker so that we finish this up in the required time. So you would notice the reaction is only occurring in the beaker, but the heat is given out of the beaker from all sides, so much so the react temperature goes up. Make sense?
Yes.
So which reactions are exothermic? We are going to set up a certain set of reactions for you so that you can remember them and you can remember those reactions as exothermic reactions. Most of the combustion reactions are exothermic. Any reactions that produces a flame, that produces fire, is exothermic. Burning things produces heat energy, exothermic. Burning a piece of paper, exothermic. Burning a piece of wood or a piece of coal, exothermic. I hope that makes much more sense now, right?
Yes.
Okay, so moving on. Hydrogen, when burns in oxygen, produces water. It also produces a lot of heat. Even though we are producing water, but this is a combustion reaction, it also produces heat. Apart from burning, other exothermic changes includes reactions of metals with acids. This is covered in unit 2. Neutralization reactions, which are basically reactions of acids plus alkalis, right? These are also neutralization reactions and they're all exothermic. Displacement reactions, which we have studied back in the reactivity or series or the reactivity of metals chapter. And those are also exothermic reactions. Rings a bell?
Yes.
Good. So apart from these, let's take more examples. Reactions of metals with acids. Most of these are exothermic reactions. For example, when magnesium is reacting with dilute sulfuric acid, the mixture gets warm since this reaction is an exothermic reaction. This is also discussed in the previous unit. Neutralization reaction. An alkali, as I just said, an alkali is reacting with an acid and it's producing salt and it's producing water. It's an exothermic reaction since the temperature of this reaction rises. And we even performed an experiment about it in the said chapter, right?
Yes.
Okay, moving on. We were also talking about displacement reaction. Let's take an example for it. Thermite reaction is a good example in which we are taking powdered aluminum and iron 3 oxide. Now, you probably already know from the reactivity series, aluminum is more reactive and iron in comparison is less reactive, since aluminum is present on the top of reactivity series as compared to iron. Iron is present at the bottom of it. So iron is less reactive. So in this reaction, definitely aluminum can displace iron. So you would see aluminum is alone as a solid. Iron is present in the form of a compound. You would notice iron gets alone after the reaction is completed, and aluminum has taken its place or displaced it to form a compound. Make sense?
Yes.
Good, great. So now every reaction we have noted up top has been considered with an example. So I hope you would remember these specific examples on top of combustion as the examples for exothermic reactions. No matter which metal they are reacting with which acid, or no matter which alkali is reacting with which acid, or no matter what kind of displacement reaction it is, which metals it's involving in those displacement reactions, you are going to consider all of those as exothermic reactions. So this way, whenever you see a reaction in these terms, you can always write in paper about it that it's an exothermic reaction, it's going to give out heat, and it's going to increase the temperatures of surrounding. If that's understandable, let's move on. Is it?
Yes.
Good. Now let's come to the next topic, which is going to be a little bit calculative. So let's first define it with theory, and then we're going to talk about it mathematics. Enthalpy change of a reaction. When I use the word enthalpy change, it needs a little description. Let's describe it first. The amount of heat energy taken in while a reaction happens or released out to the surrounding or during a chemical reaction, we call it enthalpy change. We define it with a symbol H. Actually, we denote it with the help of symbol delta H. Now, this small triangle is pronounced as delta. We use a capital H and never a small h. This triangle means, this delta means change in. So this simply means delta H means change in heat, which means probably either this reaction has given out some heat or taken in some heat. Now, we have described reactions as giving out heat as exothermic reactions. Don't forget, for heat energy taken in, we are yet to describe those kinds of reactions. So let's wait for a while, and after this topic, we're going to get to that. Make sense?
Yes.
All right, great. So enthalpy change actually would be the amount of heat energy, and we're going to calculate that, which is given out or taken in a chemical reaction. It is actually the difference between the energy of the products and energy of the reactants. So now you are going to assume that there is a certain chemical energy present in the reactants and also in the products. Whatever the changes are, whether the reaction has given out some heat energy or taken in some heat energy, that's because the energy of reactants and energy of products is different. So how do you show that? How do you express that? Let's learn that. Delta H is given a minus or a plus sign to show whether the heat is being given out or absorbed by the reaction respectively, which means whenever there is an exothermic reaction, delta H is given a negative number. Why? Because the reactants will lose some of their energy as heat energy to the surroundings. That heat is transferred or dissipated to the surroundings, and their temperature rises, which we simply tell as they're getting warmer. As I was giving the example of coal, which means coal has some specific chemical energy in it. When we start burning coal, it gives out that chemical energy in the form of heat energy, and the surroundings start getting warmer. That's when we really like the barbecues or the bonfires. I hope that makes sense, right?
Yes.
Good. So delta H is measured in kilojoules per mole, which means kilojoules would be the unit of heat energy. Joules is actually the unit, kilojoules is simply thousands of joules. Kilo means thousand. And per mole means the quantity of substance taken as moles, not as grams, not as decimeter cubes, but as moles, which we put out as standard unit for the amount of substance back in unit 1. I hope you remember it from unit 1, right?
Yes.
Good.
Can you give me 1 second?
Yeah, sure. Take your time. All right. So let's take an example. Magnesium is reacting with dilute sulfuric acid. It's producing a salt. It's also producing hydrogen gas with it. The reaction is shown as delta H is equal to negative 466.9 kilojoule per mole. What does that mean? First of all, this negative sign should tell you that this is an exothermic reaction and the heat is being given out. That's the first thing you should notice about any reaction around which this delta H value is written. Next to it are specific numbers and kilojoules, which means 466.9 kilojoules is the amount of heat energy which is given out. And this per mole means that 1 mole of magnesium reacts with it. Since the equation tells us that 1 mole of magnesium reacts with 1 mole of sulfuric acid, so that's the amounts that we are going to consider for this specific reaction, since it's a balanced chemical equation. So 1 mole of these substances, when they react, they produce this much amount of heat energy, which is given out for this specific reaction. Make sense?
Yes.
Now, you may write these like this, kilojoule per mole, or like this. It's just a difference of notation. And I hope you understand both notations from mathematics. So I hope you understand whether we write a per sign or whether we write the standard notation of -1. It is actually the same thing. So how do we show it in the form of diagram? Since this is a mathematical value, we have also a way of showing it in a diagram. Let's take a look at this diagram. So as soon as the reaction proceeds on x-axis, which you would see over here, there are some energy changes on the y-axis. Take a look. The reactants have a higher energy, right? And the products have a lower energy, right? Why is that? Because some of the heat energy is given out to the surroundings. And since there is a decrease in energy, we show it by a downward arrow. Now keep this in mind, because this is the notion that every scientist, student, and teacher on the planet uses. So whenever there is an exothermic reaction, make sure you draw the reactants up top, the products at bottom, and you draw a downward arrow between them. If the arrow is not pointed downwards, it would be considered as a mistake. All right. What is this trying to tell us? This is trying to tell us that reactants have more chemical energy. Products have less chemical energy. Remember, the ones that have less chemical energy are more stable since they're forming after chemical reaction. This is also telling us that there is a downward arrow. The heat is given, the energy is given out in the form of heat. And that energy is going to warm up both the reaction itself and its surroundings. So if you were supposed to write the upward equation over here, you would write it like this. You would write magnesium over here plus sulfuric acid over here. Instead of reactants, remember, this is just a generic diagram. Every time you are coming up with a reaction, the reactants word is replaced with these. Also, the word products would be replaced with the actual products that we form after that reaction, which was this and this. I hope that makes sense.
Yes.
So every time you have this reaction written with you up top, can you convert it into this diagram if required by the question? I think that's pretty easy, right? Since you write the reactants on top, products at bottom, an arrow pointed downwards, the x-axis is always progress of reaction, the y-axis is always energy. I guess that's easy. You would practice it with a couple of questions, and I hope you will be able to do it flawlessly, right?
Yes.
Sometimes students tend to write the energy units along with that. I mean, they can write kilojoule per mole over here, and it's perfectly fine to write the units on y-axis, since we're dealing with these units, and I've already explained it over here, right?
Yes.
Okay, moving on. And I said earlier that there is another type of reactions which we're still supposed to explain. So let's come to that. Endothermic reaction. Now this is the other kind. This is the one which absorbs heat from the surroundings. These are said to be endothermic. If you hold a test tube, which is in which an endothermic reaction is going on, you would notice it gets colder. For example, sometimes when we are playing and we get ourselves in an accident and you use a cold pack. What is cold pack? Cold pack consists of chemicals which after reacting, they exactly are going through an endothermic reaction. The cold pack would absorb heat from the surrounding and they would reduce the temperature of the arm. This gives you a cold feeling. You can tell then and there that there is some endothermic reaction going on, right?
Yeah.
Okay. In order to explain it, elaborate it further, endothermic reaction is exactly opposite to exothermic reaction. Take a look. When we were discussing the diagram, reactants had more energy, products had less. Endothermic, if opposite, products would have more energy and reactants would have less. So which means it would be something like this. Reactants at bottom, right? Products on top, and the arrow in between should be pointed upwards, exactly opposite to this one. Make sense?
So
And
the reactants have less energy?
right, the reactants have less energy, the products have high energy. Remember, the same x-axis and the same y-axis would be here too. There would be no change in that. The only changes would be reactants have lower energy, products have higher, and the arrow is pointed upwards, which means they have taken in energy, heat energy from the surroundings. That's why the surrounding tend to get a little bit colder, and we can feel it from a cold pack even, right?
Yeah.
Good, good. Let's explain it further with the help of diagrams. You would notice in this kind of reaction, the heat is taken in from all sides. The temperature goes down. The heat energy is then used literally to convert it into chemical energy. Just give me a second. Sorry for the interruption. I'm back. So I was saying the heat energy was literally used to convert it into chemical energy, energy stored in the bonds of chemicals. That's how the reactants, even having less energy, were able to be converted into products. All right. So let's elaborate it further. It would make much more sense after. The temperature of the reaction mixture and surrounding goes down. Heat has been used and been converted into a different form of energy. We usually see this in thermal decomposition reactions. Now, you might have noticed thermal decomposition reactions, but that is from a different unit. Unit 2, we discuss some of these reactions. Let me take examples of those reactions. The first one, copper carbonate. It's a green colored compound. When we heat it, it gives us a black colored compound, which is copper 2 oxide. It also gives out a colorless gas, carbon dioxide. This is a thermal decomposition reaction. Decomposition means to break down one compound into multiple compounds. And thermal means that breakdown was carried out with the help of heat, like we did in this experiment. We can also do the same with zinc carbonate. It also is decomposed into zinc oxide and carbon dioxide when heated. So one compound is broken down into multiple compounds, decomposition, on the basis of heat, thermal decomposition. These are the examples of endothermic reactions. So every time you face a thermal decomposition reaction and a single reactant is converted into multiple products with the help of heat, you would consider it as an endothermic reaction. All right. There is one important thing we need to keep reminded of. Not all reactions that have to be heated are endothermic reactions. Sometimes we just heat something to make it go faster, and we'll study it in the upcoming chapters. Okay, let's show it with the help of a diagram. Since we already did this diagram, I don't think this should be a problem, right?
Yeah.
In this case, remember a couple of facts. Reactants have lower energy, products have higher energy, arrow is always directed upwards, products are less stable, reactants are more stable. Remember, the one that is on a lower position, always stable. Be that reactants or products, the one at a lower energy level is always going to be more stable. All right. Not just that, one most important thing, when we are going to write this reaction, it would be given a plus sign, a positive sign. So it's pretty easy. Negative sign, exothermic reactions. Positive sign, endothermic reactions. Make sense?
Yes.
Now, since it's kilojoules per mole, you should be able to understand that we have taken 1 mole of calcium carbonate in this reaction and converted it into its respective products. So 178 kilojoules of heat energy was taken in before we could break that down. So any lesser amount of energy won't be able to decompose it. The exact amount of energy or higher would be able to decompose it. Make sense?
Yes.
Great. Let's move on. Let's discuss how we can measure enthalpy changes mathematically after performing an experiment in lab. How we can measure how much heat is taken in or given out in a chemical reaction when we actually perform it in lab. Let's discuss that. So before we discuss it, we need to understand one thing: specific heat capacity. Specific heat capacity is something that we study in physics as well as in chemistry, hence the part physical chemistry. It's actually related to both subjects. Defining specific heat capacity, it tells us how much energy has to be put to increase the temperature of something. When we discuss specific heat capacity, in chemistry, we pretty much stick to the specific heat capacity of water, and that's about it. So specific heat capacity of a substance is defined as the amount of heat needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. So if we're talking about water, the specific heat capacity of water would be the amount of heat needed to raise the temperature of 1 gram of water by 1 degree centigrade. And the exact value for this is 4.18 joules per gram per degree centigrade. I hope that makes much more sense now. Since 4.18 joules would be the energy required to raise the temperature of 1 gram of water, since there is per gram, by 1 degree centigrade, since there is per degree centigrade too. Right? So what if we have to increase the temperature of 1 gram of water by 2 degrees centigrade? So it would be multiplied by 2. What if we have 2 grams of water? Then it would be multiplied by 2 again. So every time you have more amount of water, or more is the temperature that you want to raise it to, you would keep on multiplying it by 4.18 value, and you will get your answer. Right?
Yeah.
Okay. Again, we are using the delta symbol to indicate a change, but this time it's a temperature change. Concepts of specific heat capacity also applies to cooling of a substance. For example, to cool 1 gram of water by 1 degree centigrade, we need to take out 4.18 joules of energy. So it's the same amount we require to increase the temperature of the substance or to decrease it. All right, makes sense?
Yes.
Let's come to the formula that we're going to use it in exams. So the amount of heat energy change would be represented as Q, the mass of the substance with small m, the specific heat capacity of it by small c, and the temperature change by delta T. So basically, what do we need? We need to know what is the mass of the substance that we are using to heat up or cooling down, and what exactly is the temperature change. We already know the specific heat for water, and we can simply calculate heat energy or that kind of change. All right. Okay, let's, for practice, do an example. Let's say we have 10 grams of water and we need to increase its temperature from 25 degrees centigrade to 30 degrees centigrade. What would be the value for Q? Don't just get me
10.
the answer. Just try telling me what you would do.
So 10
Right?
times
10 times what? The value of C would be
25.
the value of C, specific heat capacity, since that's a fixed number for water, and that is
4.18.
4.18. So it's 10 times 4.18. So how many degrees of temperature did we increase it to? Remember, this is delta T, and delta T means we are going to subtract these two in order to get our answer. So the answer would be
5.
5 degrees Celsius. So that are the three numbers that we're going to multiply in order to get the value for Q. Make sense?
Yeah.
Right, pretty easy. These kind of questions have been a part of past papers, and I think these are very easy to get, but we are supposed to combine it with an actual experiment in lab. So what are those experiments called as? We commonly call them as calorimetry. Calorimetry are the kind of experiments in which we measure the amount of heat absorbed or given out in chemical reactions or physical changes. The technique is calorimetry, and it's based on the idea that heat of reaction for any chemical reaction or a physical change has been changed, means either the temperature went up, it was an exothermic change, or the temperature went down, it was an endothermic change. So we have this equation in order to calculate the exact amount of heat released or absorbed. So what do? We work with the moles of reactants in order to actually calculate the molar enthalpy change, since delta H every time is measured in kilojoules per mole. So how do we do it? We actually try to calculate how much heat energy is released or absorbed when 1 mole of any substance goes through a chemical reaction. In this reaction, we are going to combust alcohol. We are simply going to burn some alcohol. So we are going to notice when 1 mole of alcohol burns, what happens. Let's go for an actual experiment. Now, measuring enthalpy changes in combustion reactions. We're going to notice of the amount of heat given off when alcohols are burned. This is a part of IGCSE. Now, we are going to talk about chapter 22 for alcohols. For now, just the name is enough for the alcohol. Now, what do? We take alcohols in small spirit burners and we then burn them. The heat produced is used to heat some water in a copper can, and we call it a calorimeter. So what do? We measure 100 cubic centimeter of cold water using a measuring cylinder, and we transfer it to the water in a copper can. We transfer this water to the copper can. We notice the initial temperature of water. Say it was 25 degrees centigrade. In fact, they are going to take a value on the next page. Now, with the spirit burner in which alcohol is present with its lids on, the lid should be kept on when the wick is not lit to prevent the alcohol from evaporating, since alcohol can evaporate. So there's the diagram. It would be much easier for you to understand through diagram. So this is the wick which we are using for burning. This is the alcohol which is going to rise up the wick and get burnt over here. This is the lid. We're going to keep the lid on so that the alcohol does not evaporate without burning. We're going to set up the apparatus in such a way that we take 1 mole of alcohol over here. We take exactly 100 cubic centimeter of water in this beaker with the help of a measuring cylinder so that we take exact amount. We also insulate it with an insulating card or a lid. Then we put the thermometer in. We notice the initial temperature of water. We start burning the alcohol. And when you have a specific amount burnt out. Let's go through line by line so that it's easier for you. Arrange the apparatus in the figure shown. The spirit burner can be used to heat the water in the copper can. The apparatus is shielded with the help of a draught shield as much as we can to make sure that the heat produced from this is used to heat up water and is not wasted outside. Light the wick to heat the water. Stop heating when you have reasonable temperature rise, say about 40 degrees centigrade, right? And then we extinguish by putting the lid back on the wick. You can simply put the lid back on the wick and you can extinguish it off. Stir the water thoroughly and measure the maximum temperature of water, since we also measured the initial temperature. Weigh the spirit burner again with its lid on so that you would know how much of the alcohol has been burned. The experiment can be repeated with the same alcohol for reliability. You may even carry out with different alcohols if they're available. So how do we note how much temperature has been increased, or what is the exact heat change? Let's calculate that. So the volume of water is 100 cubic centimeter. Mass of burner plus alcohol before experiment was this, after experiment was this. So there is a very small change in it. Original temperature of water that we started off with was this. The final temperature of water was this. How do we know? We use this equation. So the delta T, as we practiced before, is 41.3 degrees centigrade. I hope that makes sense, right? Subtracting
Yes.
these two values makes sense. Now, what about the mass? Since we have taken water in volume, that can be a pretty tricky, but we have something very simple to solve it up. Mass of water is actually 100 grams. Why? We have taken water intentionally because the density of water is 1. When we multiply density with volume, we have the mass, which does not change. So the amount of water in volume remains same as in mass. Thus, it's just a difference of units. So if you take 50 cubic centimeter of water, if it is converted into grams, into mass, it has to be simply multiplied by 1. It is then 50 grams. Make sense? That's why we took water in the first place. It's easier to work with water, right?
Yeah.
Good, good. Moving on, let me clear it up and let's finish this entire equation. So you know the value of C. The value of C is fixed for water. That is 4.18. Memorize this value as soon as you can for your ease. So let's put up the numbers. 100 was the gram of water we took. This is the specific heat of water. This is the change in temperature. This is the amount of joules of energy produced. Since these are just joules, in order to convert them into kilojoules, we divide them by 1,000 and we get the number. So this is kilojoules, amount of energy given out by this reaction. But that's not exactly kilojoule per mole. You won't see the symbol kilojoule per mole over here. Why? We haven't worked out the number of moles yet. Now let's talk about that. Ethanol has this formula. If we talk about the MR of ethanol, we need to work it out, and that's given over here, which is 46. You know how to calculate MR, so that shouldn't be a problem, right?
Yeah.
Since carbon's 12, hydrogen's 1, oxygen's 16, it's easy to calculate. The masses are this and this. We started off with this mass of ethanol, we ended up with this mass, so we have burned this much amount of it. Let's take out the number of moles. I hope you remember that the formula for moles was mass over MR, right?
Yes.
So this many is the amount of moles of alcohol that we have actually burned. In order to calculate per mole of value, it's pretty easy. Divide the heat in kilojoules by the amount of moles that you have just calculated, and you would know the exact amount in kilojoules per mole that an alcohol gives out when we burn it. And we use the exactly similar way for any substance that is burned and the energy is calculated. Make sense?
Yeah.
This is the equation for that alcohol. That alcohol was burned in the presence of oxygen. It produced carbon dioxide and water. We're going to learn this equation in unit topic 22. So let's now, that as that is a part of unit 4, forget it how we come up with this equation, but focus on this stuff. As the heat was given out, it increased the temperature of water. We are to make sure that we put a negative sign before we write these numbers. This 1020 kilojoule per mole, delta H is equal to negative of it. Why? This was an exothermic reaction. Why? Because the temperature of water went up and not down. If the temperature of water went down, we are supposed to use a positive sign before these numbers. Make sense?
Yes.
Good, good, great. Now, a key point. The enthalpy change when 1 mole of the substance is burned is known as enthalpy change of combustion. And we can find enthalpy changes of many different reactions. We can find enthalpy change of combustion. We can find enthalpy change of neutralization as well. Okay. Now, make sure that you follow the 3 significant figures rule. You should write at least 3 significant figures with this kind of value, right? Also, don't forget the hint. If the reaction is exothermic and the temperature is increasing, we use a negative sign. And if the reaction is endothermic and the temperature is decreasing, we use a positive sign, as mentioned over here, right? As we just discussed.
Yeah.
Okay. Evaluation of experimental results. How accurate were your results? To be honest, your results were 1 or 2, while in data booklets, the values you are given, the booklets you are given in exams for any values will have this value. Now, where does this number comes from? This number comes from the very, very perfect kind of way this experiment was taken out. Now, in lab, you cannot use all of that heat to increase the temperature of water and minimize the wastage to 0. That is very difficult for us in a school lab. However, for sophisticated labs, this isn't a problem. So you would notice they have a bigger value over here, which automatically tells us there were many sources of error in our experiment. For example, a lot of heat was lost to the environment. Some of the heat was given out to air. Some of the heat was lost directly from the flame. And it went to the air rather than into the water. Some of the heat was used to raise the temperature of copper can and the thermometer as well. Right?
Yes.
So these were our sources of error if ever asked in exams. So make sure that you remember these 3-4 sources of error. Also, sometimes there is incomplete combustion of alcohol, which is really a part of another chapter. Sometimes we don't have enough oxygen. We don't release as much heat energy as we're supposed to. Instead, we go for a yellow-orange flame. Sometimes you see a few things burning with a yellow-orange flame. This means we don't have enough oxygen. Sometimes you can see the flame color is blue, right? So blue means that you have enough oxygen to burn it completely. Yellow means you don't have enough oxygen. And sometimes black particles are also produced at the bottom of copper can. This means the combustion can be different for different experiments, and that can also be a source of error. I'm not discussing this topic in detail since it does not belong to your syllabus, since that is unit 4, and they won't ask you a question from unit 4, all right? That's why I'm intentionally skipping it. Make sense?
Yeah.
If you remember this part for your current exams, this would work enough. Don't try remembering this part because they won't ask you this since it's out of course for you. All right. However, when we'll do unit 4, I'll go through that portion, no problem. Now, extension work. A bomb calorimeter is actually used to calculate more accurate values for enthalpy changes of combustion. The substance is ignited electrically. We actually ignite it with a spark and not with a flame. And it is burned in the presence of pure oxygen instead of air. That heat is transferred to both water and the calorimeter itself to give us a very accurate change. All right.
Okay.
So this gives us a very good idea about the structure of alcohols and how much heat is released. Again, this is all a part of unit 4, so I am skipping it for now. Right? Okay, good, good. And this also is a part of unit 4, so we're not doing it now. I'm skipping any parts like that since they won't be a part of your exam, since it's out of course for you. Now, working out enthalpy changes for reactions that using solutions instead of this burning for calorimeter experiments, like I was talking about displacement reactions or neutralization reactions. So how do we do them? Let's do another experiment. It's pretty easy. Now we take a polystyrene cup, since it's made out of an insulator. We'll put it in a 250 cubic centimeter glass beaker. We transfer 50 cubic centimeter of a specific amount of solution. We are going to go with a displacement reaction into the polystyrene cup. Now weigh 1.2 grams of zinc on a weighing board on a balance. Record the initial temperature of your copper 2 sulfate solution. Add the zinc. Stir the solution as quickly as possible. Record the maximum temperature reached, and even stir it with the help of thermometer. Don't use a separate stirrer, since that would involve both your hands. And doing it with one hand and reading the temperature is easier for students to do the entire experiment. It's as simple as that. What do? We note the initial temperature, we note the maximum temperature. You would notice there is a temperature difference. So how much is the amount we have? Since we were working with a solution and we used 50 cubic centimeter for it, so we're going to convert it into 50 grams. 50 cubic centimeter of a solution would be 50 grams. Pretty easy, right?
Yes.
Why? Because the density of any solution in water is same as that of water. The amount of salt is so less that we can neglect it simply. So 50 cubic centimeter of water is 50 grams of water. That's where we have it. 4.18 is the specific heat capacity for water. And this is the temperature difference. Calculate the joules, divide them by 1,000 to get the amount of kilojoules, right?
Yeah.
What we still need to work out the per mole part. Okay, so let's work it out on the next page. And let's quickly finish this chapter, since after this, we'll finish the chapter quickly. Okay, so number of moles of zinc added, mass over molar mass, right? So 1.2 grams of zinc was added, and the atomic mass, relative atomic mass for zinc in the periodic table is 65. Divide these values, you'll get your answer. Number of moles of copper 2 sulfate, volume into concentration, 50 cubic centimeter was the volume. This is the concentration, so this many moles. So we need to calculate how much heat is released when 1 mole of copper 2 sulfate reacts with excess of zinc. So we take this value and divide it by this. Why do we take the value of copper sulfate? Because the zinc was in excess. Remember, we have studied back in the moles chapter, when there is one component that is present in limiting amount, which is copper over here, and one component which is present in excess amount, our calculations are always made with the help of limiting reactant and not with the excess reactant. I hope you remember that back from unit 1, right?
Yes.
Great. So you know which value you need to divide it with, and you get your answers in kilojoules per mole. Since that's the amount of heat energy given out and the temperature of water increased, so we are supposed to put a negative before it. And that's the exact equation for it. My bad. That's the exact equation for it. Right? I've already explained the key point of excess in limiting. I've already explained the 1,000 part in the moles chapter, that we convert This was 50 cubic centimeter. We divide it by 1,000 to get a value in decimeter cube. And decimeter cube is the standard unit that we work with in volume. I've also explained it back in the moles chapter. All right. Good. Great. Great. Let's clear it up and move forward. Last activity. I think this is not even the last activity. Okay. So activity number 3, measuring the enthalpy changes when salts dissolve in water. We pretty much do the same thing when we dissolve a salt in water. Polystyrene cup, specific glass beaker, transfer exact amount of water, record the initial temperature, weigh a specific amount of salt, make sure the salt is in excess, and then dissolve it, stir the solution vigorously, keep noting the temperature change until all of the salt has dissolved, and then note the minimum temperature. Minimum temperature, why are we talking about minimum temperature? Since in this case, the temperature decreases, which automatically gives you the idea this was an endothermic reaction. Make sense?
Yes.
Good, good. Since we started off with 100 cubic centimeter of water, so it's 100 grams mass, specific heat capacity of water, and this time we're going to note the difference of water in a decreasing value. Since it's an endothermic reaction, it gives out the heat change in joules, and we divide it by 1,000 to get the value in kilojoules. Let's work out for moles of the substance. Now, working it out requires 2 steps like we did in the previous go. For ammonium chloride, we work out the MR. This is 53.5 from its formula NH4Cl. And we had 5.2 grams of ammonium chloride. This is the number of moles, right? And we divide it by the same value. Sorry, it's not the salt in excess, it's actually the water is in excess. My bad. That's why we are dividing it by the value of salt. All right. I hope that makes sense. As I've already cleared, whatever is present in a limiting amount, we are going to keep our calculations according to that. And whatever is present in excess, we will not calculate according to it. Since water is in excess, we are not calculating according to that. And we are only going with the calculations according to the salt, since the salt is the limiting amount over here. I hope that makes sense. And we get our value for kilojoules per mole, but this time it's written with a positive sign. Why? The reaction was endothermic. And since only we dissolved it, you would notice the equation has same components on left and right. It's just that from solid salt, it has turned into an aqueous solution, which gives us the idea that dissolving is a physical process, but sometimes the physical process can also be bifurcated into exothermic processes and endothermic processes. So sometimes some salts are dissolved in water, heat is given out, but then there are some other salts like ammonium chloride, which are when dissolved in water, take heat in, meaning the process is endothermic. Make sense?
Yes.
Finally, I guess this is the last activity. Yeah, neutralization. So neutralization can be reaction between alkali and as an acid. Every alkali has OH negative ions. Every acid has H positive ions, as explained in previous unit 2, and they react to give out a salt and water. Only the H and OH negative ions react to form water. The other ions react to form salt. We are not going to discuss about salt. We are only going to keep it with respect of water. Let's go with almost the same reaction. Polystyrene cup in a glass beaker, exact amount volume of exact concentration of alkali transferred to the polystyrene cup, record the initial temperature, fill a burette with 50 cubic centimeter of your acid, use the burette to add 5 cubic centimeter of acid, stir vigorously, record the maximum temperature, continue adding 5 cubic centimeter portions of dilute hydrochloric acid, continue stirring and recording the maximum temperature each time until the total volume of 50 cubic centimeter has been added. Now, you are supposed to calculate its value with the help of a graph. Let's take a look at that graph. Now, you would notice the graph has volume of acid added on in cubic centimeter on x-axis. However, the temperature of the mixture on y-axis in degrees centigrade. Now, as soon as you keep adding the volume of acid, you would notice the temperature keep going up. It rises until it gets to a highest point, then it starts going down. Why? In the start of the reaction, the acid is being used to neutralize the alkali, the temperature goes up. Heat is given out. But when the neutralization is complete, and this happens exactly at this highest point, since there is no more neutralization, we are just adding acid to salt and water, nothing happens, the temperature goes down by giving out heat to its surrounding. So we have two best fit lines on the graph. The point where the lines cross one another, actually intersect one another, is the maximum point, temperature point, and that specific temperature point in this case is 31.8 degrees centigrade. And at that point, the exact amount of acid used is 28.00 cubic centimeter, right? Now you would
Yeah.
understand why we have involved the graph. We have involved the graph to find out the maximum temperature reached and the amount of acid used exactly at that temperature. Because it would be very difficult, since we were adding portions of 5 cubic centimeter, we would never know how much the exact amount of acid was added. So the graph helps us with calculating the amount of acid added as well as the highest temperature reached. Since we have the values with us now, let's move on with our calculations. Again, the same formula, Q is equal to MC delta T. Now, that is 53. Now, remember, the alkali was 25 cubic centimeter, the acid was 28 cubic centimeter, the overall volume is 53, and that is quickly converted into grams, and we use 53 grams over here. Specific heat of water, 4.18. The difference in temperature, this much. You get the value in joules, divided by 1,000, you get the value in kilojoules. Now here we assume two things as we have been assuming previously. Density of the reaction mixture is same as that of water since we are producing water by reacting acid and alkali. So 1 cubic centimeter is equal to 1 gram. Specific heat capacity of the mixture is same as that of water. It's a fairly reasonable assumption. So neutralization solution is mostly water. Although there is a little bit amount of salt, but we seriously ignore that and continue with our calculation. Now, the number of moles of KOH are concentration into volume. The concentration was 2 moles per decimeter cube. The volume was 25 cubic centimeter divided by this, and you get the number of moles of KOH used. Moving on, number of moles of HCl will be exactly the same since the temperature was taken as neutralization point. So what do? We use that molar value of KOH divided by the overall number, we get our amount in kilojoule per mole. So for this exact reaction, the heat given out is 55.4 kilojoules per mole. Since the temperature increased, it would be shown with a negative sign and the heat was given out. Now, we also might sometimes need to calculate the HCl concentration. We can do that by this experiment easily. 28 cubic centimeter of HCl, and this was the number of moles of HCl used. So we can calculate the concentration by moles over volume, and I think this is pretty easy. Remember, this is 28 cubic centimeter, and you are supposed to divide it with 1,000 before you put the value in this formula, since we're taking decimeter cube in this formula, right? So this was the concentration of acid used. Make sense?
Yes.
One of the last points of this chapter. Why do reactions either give out or absorb heat? Let me take a look at this. There are a few pages left, and So why do chemical reactions either give out or absorb heat? Why do we have to essentially bifurcate them into exothermic or endothermic reactions? Now, this bifurcation is essential since every chemical reaction, the bonds have to be broken in the reactants and the new bonds have to be formed in the products. Now, uh, every chemical reaction is actually composed of these two steps. Now, if every chemical reaction is composed of these two steps, breaking of bonds, which is necessarily an endothermic process since it requires energy, and formation of new bonds, which is necessarily exothermic process since it releases energy. So why do we bifurcate them into separate categories since every reaction is composed of both? Now, here's how we are going to explain it. Now, the reaction you see in an example for explanation is combination of hydrogen with oxygen to form water. What they are trying to say is that breaking these bonds in hydrogen and oxygen is an endothermic process. And for the same part of the reaction, formation of new bonds for water is an exothermic process. So take a look at this diagram. You would notice there are two molecules of hydrogen. Both have a single covalent bond. There is one molecule of oxygen which has a double bond. And all of these bonds are broken down, this one, this one, this one, and we form new bonds. We're actually forming two molecules of water, and for every molecule of water, you would find two single covalent bonds. Oxygen is making a bond with hydrogen here, and oxygen is making a bond with hydrogen here too. This is for just one molecule of water. So we broke a few bonds and we made some new ones. And this part of the process was endothermic. It required to absorb some energy. This part of the process was exothermic. This released some energy. Now, how do we came up with the suggestion that the overall reaction was exothermic? Now, since I am saying this because we have studied it on the previous pages that the formation of water from hydrogen and oxygen is exothermic. So how is it exothermic exactly? Let's clear it up. Let's move on. So energy has to be supplied to break the bonds in hydrogen molecules and oxygen molecules, and the energy is released when hydrogen and oxygen atoms form new bonds in water molecules. In this particular reactions, the products are more stable than the reactants, which means the total amount of energy released, since it's an exothermic reaction, when covalent bonds are formed in water molecules is more than what's required to break in the covalent bonds, which we require to break in hydrogen and oxygen. So the reaction is exothermic. So what they're trying to say is this endothermic value was smaller as compared to this exothermic value, which was bigger. And it's pretty easy to understand. This smaller and bigger comparison seems a little difficult when we do it in the form of diagrams. The smaller and bigger comparison seems extremely easy when you do it with numbers. Now, what happens when you subtract a bigger number from a smaller number? Isn't your answer comes out to be negative? It does, right?
Yes.
So don't you remember negative something when we talked about delta H, we posed negative as exothermic. Make sense?
Yes.
So at the start of the reaction, since breaking of bonds is the start of this reaction, we absorb some energy, but that absorption is pretty small in its values. And by the end of the reaction, when we are done forming new bonds, we release a lot of energy, which definitely has some bigger value. Since we take a difference of these two values, our overall energy for the reaction turns out to be negative, which proves the reaction to be exothermic. Let's take another example. When you heat calcium carbonate, which if you remember from the previous pages, was a thermal decomposition reaction, since we break down one calcium carbonate a molecule, or you can say one compound, into multiple compounds. using heat. Now, breaking up the original bonds using more energy, and the bonds that we obtain produce less. So what happens? The reactants are more stable than the products. This means when the reaction is finished, more energy has been absorbed than is released. So we call it an endothermic change. So let's finalize that. So definitely for exothermic processes, the breaking of bonds has a smaller value, which was endothermic, by the way, and the formation of new bonds has a bigger value, right? That's how we end up having an reaction bifurcated as exothermic reaction. But for endothermic reactions, this is actually the opposite. Breaking of bonds is a bigger value, and formation of bonds is a smaller value, since we're adding up absorbing more energy for the reaction than what's released. I hope that makes sense, right?
Yes.
Good, great. So since we're just talking in words, how would we be able to calculate the enthalpy changes with actual bond energies? I mean to say, how are we going to do all of this mathematically? Let's do it mathematically. Before we do, we need to go with one very important definition, and that is bond energies. Breaking chemical bond requires energy. Stronger the bond, more is the energy needed to break it. Bond energies are also measured in kilojoules per mole. For example, the Cl-Cl bond energy is 243 kilojoules per mole, which means if we want to break all the Cl-Cl bonds in 1 mole of chlorine gas, we would require 243 kilojoules of energy. So that's pretty simple. Every bond can be explained in terms of its bond energy, which means if you need to break the bond in 1 mole of its molecules, 1 mole of bonds, you would require that much amount of energy. And it's pretty simple since it's a cyclic process. Let's understand it with the help of this diagram. Now, this is a chlorine-chlorine single bond, and we have been saying that it requires 243 kilojoules per mole for 1 mole of these bonds to be broken down. So as soon as it absorbs this energy, all the single bonds in 1 mole of these bonds are broken down since they have got their energy, and we get 2 separate atoms of chlorine. But when these 2 atoms combine together to react to form chlorine molecules, they release the same amount of energy. So this is a cyclic process. Once the bond is formed, the exact same amount of energy is released, which if you give back to the bond, it would break again, right? So that
Yes.
means the bonds, when they form, they release the same amount of energy, which they after require if we want to break that bond again, which means the energy is going to be same on both sides. It's just that when we are breaking the bond, that energy becomes positive since it's going to be absorbed. And when we are forming a new bond, that energy would be negative since the energy, the same amount of energy would be released. So breaking of bonds, endothermic always. Making of bonds, exothermic always. In a similar way, if we talk about other kinds of bonds and their energies, let's talk about a few more examples. You would notice that an HCl bond energy is 432 kilojoules per mole, right? So if you see the HCl gas in an equation, you would notice you require 2 into 432 kilojoules to break all the HCl bonds in 2 moles of hydrogen and chlorine gas. I hope you understand. If you don't, let's write the equation over here to help us with it. This is the equation for formation of HCl. Since hydrogen and chlorine are gases, they also produce the gas hydrogen fluoride. Now, what they're trying to say is that this bond energy is actually 400 kilojoule per mole. But for this balanced chemical equation, we actually have 2 moles So we require 2 into 432 kilojoules of energy to break all the bonds in HCl for 2 moles of HCl. Right? Make sense?
Yes.
All right. So take a look. They have given many different bond energies: carbon and hydrogen, carbon and chlorine, carbon and iodine, iodine and iodine, hydrogen and chlorine, finally hydrogen and iodine. So you would notice the energies are different for different bonds. Finalizing it, let's define bond energy again. The amount of energy needed to break 1 mole of covalent bonds in gaseous molecules is bond energy. Remember, gaseous molecules is something which is a part of definition. Why is it a part of definition? May not be something discussable at this point of time, but don't forget, this is essential for this definition, so please do not exclude it from the definition. All right, moving on. Bond energies can be used to calculate how much energy, heat energy, would be absorbed or released during reactions of covalent molecules. What happens for ionic compounds? It's beyond the requirements of IGCSE. So let's just discuss covalent compounds, and let's try and calculate from examples of few covalent molecules whether the energy is released during their formation or absorbed. All right, let's take an example before we move on to an actual one. For example, if the energy needed to break all the bonds in reactants is 1000 kilojoules, and with the positive sign, the process is endothermic. How do you come to know that? Because of the plus sign. And if the energy released when new bonds are made in products, the overall energy is negative 1200 kilojoules. This would tell you the amount of energy, but the negative sign tells you this is exothermic. Now for overall change, what would happen? The answer would be negative 200 kilojoules, which means the overall reaction was exothermic. How? Why? Because the energy taken in was much less than the energy given out when new bonds were formed. So the overall reaction is going to be exothermic. I hope you understand that since I've given a couple of examples before too, right?
Yes.
Okay, for extension work, a couple of important points. Bond energy calculations only ever give estimates of amount of heat energy evolved or absorbed. They actually never give the exact values. The strength of bond varies slightly depending upon what is around in the molecule. So actually the entire molecule is responsible for a specific bond energy. Usually the values quoted on the previous page in the table were average values. They're fairly good for calculation, but they are never the perfect answers. What are the perfect answers? The perfect answers actually come from experimental work. Calorimetry, for example. Now, let's move on to an actual example. The reaction between methane and chlorine. Now, methane is the gas we commonly use for cooking of food, and chlorine is the gas that we have studied as a poisonous gas. They both can react together to form two covalent compounds, which are CH3Cl and HCl. Now you would notice every compound in this equation is a covalent compound. We are breaking a few covalent bonds and we're making some new ones. Now, let's understand the structures first. Methane is a simple molecule with carbon in center and 4 hydrogen atoms surrounding it. Chlorine is a pretty simple molecule. We have discussed it before. CH3Cl has carbon in center. It has 3 hydrogen, but 1 chlorine atom around it. And finally, HCl. So this reaction requires ultraviolet light to proceed. This reaction happens in the presence of light. You will notice a few old bonds have been broken down and a few new ones have been made. Take a look. To explain, they first break down all the molecules. In order to break down, all the bonds. In order to break down bonds, you would notice that they use a sign like this on a bond to show you that it's broken. The zigzag sign on the bond line gives you an idea that this bond is being broken, right? You
Yes.
would notice all the bonds in methane and chlorine have been broken down to make new ones. Now, how are we supposed to calculate? Now, one simple method is to calculate all the bonds that have been broken down and all the ones that have been made new, and then finally the difference in order to calculate your answer. So we are going to do that. Take a look. We have carbon-hydrogen bonds in methane, 1, 2, 3, and 4. So we have 4 carbon-hydrogen bonds in methane. We have 1 chlorine-chlorine bond in chlorine molecule. Take the numbers, multiply them with the values we will take from the table on the previous page. The value for CH bond is 413. The value for chlorine-chlorine bond, as we have discussed before, is 243. It gives us the amount of energies that we require, since this reaction requires to absorb before the reaction is able to break down all the bonds in the reactants. The total is 1895 kilojoule. When new bonds are formed, take a look. We have 1 carbon-hydrogen, 2 carbon-hydrogen, and 3 carbon-hydrogen bonds. We have 1 carbon-chlorine bond, and we have 1 hydrogen and chlorine bond, right?
Yes.
Putting the values respectively for carbon-hydrogen, carbon-chlorine, and hydrogen-chlorine bonds, we come up with a total. Let's move a little bit. The total for this one is 2017 kilojoules. This is the amount of energy released since we are forming new bonds. Now, the total on both ends, just simply add them, you'll get your answer. If the answer is negative, your overall reaction is exothermic. If your answer is positive, your overall reaction is endothermic. Since in this case, the overall answer is negative 122 kilojoules, which means this reaction is exothermic. Make sense?
Yeah.
Okay. One important hint, when energy is given out, you put a negative sign in front of the value. When energy is taken in, you put a positive sign before the value. One very important extension work part, the real reaction doesn't actually happen by all the bonds broken in this way. That isn't important. The overall amount of heat released or absorbed is the same as long as the reactants and products are exactly the same. However, you do the reaction, even the ones of the routes you used to calculate, it is entirely imaginary. This is summarized in an important law we call Hess's law, which you are going to discuss at A levels. Hess's law is not discussed at this level. So what he's initially trying to say over here is that there are other means to calculate here too, but we consider different routes of different processes. There is one more simpler way to calculate these kinds of values. Let's go through that way. This way does not require for you to calculate all the values. Take a look. This has 1, 2, 3, 4 carbon-hydrogen bonds and 1 chlorine-chlorine bond. Okay, let's actually color them differently. 1 chlorine-chlorine bond. Let's give it a red color. Now, for the products, you have 1, 2, and 3 carbon-hydrogen bonds. You don't have any chlorine-chlorine bonds. You have 1 carbon-chlorine bond, and you have 1 hydrogen-chlorine bond. Now, for all the bonds that are similar on both sides, you may entirely skip their calculation. All right? For example, there are 3 carbon-hydrogen bonds over here and 3 carbon-hydrogen bonds over here. Do not calculate them. You can calculate this one, this one, this one, and this one, since they are the 4 ones that are different. And you would find that your values still end up as negative 122. How? Let's calculate them. Carbon-hydrogen is 413, and chlorine-chlorine is 243 on this side. Carbon-chlorine is 346. And these are positive values. Of course, these are going to be negative since they are given out. And hydrogen-chlorine is 432. If you have a calculator closer, can you calculate these values for me? Are you calculating?
Yes.
Is it similar to what we have discussed before?
Yes.
Now I've done the same thing on the screen. You would notice that your answers is the same.
Yeah.
Okay. This is a good way of doing it if you want to go for a shortcut, if you want to spend less time, and if you simply just give the examiner the overall answer, this one. But it never really calculates the actual overall values, these, and the one we calculated at the bottom. If the question requires you to calculate these values, the one, I guess it was 217 for this one, the total for this one. If the question requires you to calculate these, adopt this process. If the question only requires you to calculate this, you can adopt a smaller process to get your answer a little bit earlier and saving yourself some time. Make sense?
Yes.
Good. Great. I guess now you understand how we're going to do it. But one very important point for covalent compounds and to go with this kind of work, remember, if you know the structures, only then you can make this numbering and go for all of it. So for anything new for you in exams, what Edexcel does is that they give you the structure. For anything old, something that you have discussed in book before multiple times, like the structure of water, they're not going to draw the structure in exams. You have simply to take it out of your memory, draw it over there, and work accordingly. All right. So let's take a look. For this specific reaction, first of all, in order to break all the bonds, we absorbed 1895 kilojoules of energy. All the bonds were broken down and atoms separated as shown over here. But then the atoms started reacting differently and they made new bonds and they gave out 2017 kilojoules of energy. Since the energy given out was much more than what the energy was absorbed, the overall reaction turned out to be exothermic. This is known as an energy level diagram. As you can see on your on your left, is energy, and you would notice that the arrows show similarly as we have discussed on the previous working. The arrow is pointed upward if the reaction is endothermic. The arrow is pointed downwards if the reactions are exothermic. Make sense?
Yes.
Great. So whether you need to calculate this value or whether you need to draw this kind of diagram, you should be able to do both in exams. All right, moving on. An example involving double bonds. Now, the bond energy, let's start with an example. The bond energy of oxygen-oxygen double bond is 498 kilojoules per mole. This seems to be a little bigger than what we are dealing with before. This is the energy required to break whole of the double bond. Now you would notice that the double bond energies are higher than the single bond ones, which means you require more energy to break a double bond than you do for a single bond, which means double bonds are stronger bonds and require more energy to break. And also, at the same time, when double bonds form, they give out more energy too. I hope that makes sense since the process was cyclic, right? Let's do an example. Methane, when burned in oxygen, gives out carbon dioxide in water. All the bonds required in these diagrams, carbon, hydrogen, oxygen, oxygen, carbon and oxygen, oxygen and hydrogen, are given in the table. Don't worry, you don't have to memorize these values since every time the bond energy values will be a part of question. Now, moving on, you would notice there are 4 carbon-hydrogen bonds. So the value is multiplied by 4. There are 2 carbon-oxygen-oxygen double bonds. The value is multiplied by 2 in order to get the numbers for the endothermic part of the reaction, which means the part of the reaction where bonds are broken down by absorption of energy. And then there are 2 carbon-oxygen bonds in carbon dioxide, and there are a total of 4 oxygen-hydrogen bonds in 2 molecules of water. The values are multiplied with 2 and 4 respectively to get the overall energy change for the part of the reaction where new bonds are formed. This is the exothermic part of the reaction. When we find out the total enthalpy change, we find out this reaction to be exothermic as well, since the overall answer is negative 694 kilojoules per mole, which means more energy is given out in the formation of products in making new bonds than what was absorbed to break old bonds. I hope this makes sense too, right?
Yes.
I hope this diagram is also easy to understand, right?
Yeah.
Since it's an exothermic reactions, the reactants are on top, the products are at bottom, the arrow is pointing downward for an exothermic change, and the overall exothermic change is negative 694 kilojoules per mole, which proves that this reaction gave out more energy than what it absorbed in. There is one important point of extension work over here. The reaction has been shown with water as a gas rather than water as a liquid. The bond energies can only be used for gaseous molecules. We could only find out the enthalpy change for this reaction forming water liquid if we knew the amount of energy released in the process water gas to water liquid. But this is beyond the requirements of IGCSE. Why are we doing it? I think it's pretty simple to understand, since as soon as I defined, and I'm going to go back a couple of pages, bond energy, I hope you remember that I defined it as the amount of energy needed to break 1 mole of covalent bonds in gaseous molecules. Since we are only talking about gases, so most of the reactions will discuss all of the reactants and products as gases. So we'll be dealing with covalent molecules also in gaseous phase in order to complete these questions. I hope that makes sense, right?
Yes.
Great. Looking ahead, entropy. Now, entropy. Let's define it by taking a little bit of examples first, since entropy is better defined with the help of examples. Many reactions that we meet at IGCSE level are exothermic. Combustion and neutralization are some examples. Despite requiring a small amount of energy to get the reaction started, which we call activation energy. For example, for combustion reaction, if you want to burn methane in air, you will need to initiate the reaction with the help of a spark or a flame. This is activation energy. These reactions release heat energy overall because the products are more stable than the reactants. We have showed this on the previous graph as well. Enthalpy is certainly a driving force for the reaction to occur. However, endothermic processes do occur as well. How are we going to tell what is the driving force for them? I hope this makes sense. If not, let me go back a little. Okay. I hope you remember we have been discussing on energy level diagrams that if something is higher in energy level, this is considered to be less stable. And if something is lower at energy level, this is considered to be more stable, right?
Yes.
So the driving force for this reaction to occur is pretty simple. Things are moving from lesser stability to higher stability. I hope that makes sense. But what for an endothermic reaction when the reactants are actually at the bottom and the products are actually on the top? What about an endothermic reaction? Which means they are moving from a more stable state to a less stable one. So that can be the driving force. Why are they moving towards a less stable state? So we need to come up with a better definition of driving force for processes like those, right? We
Yeah.
have dissolved ammonium nitrate in water, which causes the temperature of the solution to decrease, but it dissolves anyway. This is possible because of a different factor, entropy. Entropy is actually the measure of number of ways for the energy in a system to be distributed, to be divided. It is greater in more disordered system because the energy can be dispersed more flexibly. Let's take a, let's take a look at an example to explain it. Solids are packed together. There are very fewer ways of distributing energy since they are packed so closely together, they don't even have enough space to squeeze more molecules in between them. When we convert a solid into a liquid, we actually move the molecules a little bit away from one another, just a little bit. If we heat up the liquid more and more, we may be able to boil the liquid, convert it into a gas, and gas is a state of matter in which the molecules are pretty far away from one another. There is ample extra space in them, and that space can always be covered with more molecules. That's why the gases were compressible in the first place. I hope you remember all of that, right?
Yeah.
Now, if we want to talk about the
Sir,
energy, there are fewer ways of distributing energy in solids than there are
sir,
in gases. Yeah,
is it okay if I just go to the bathroom quickly?
you're sure? Go ahead. So I was saying that in solids, we have very fewer ways of distributing energy since they are so closely packed. And we have a lot more ways to distribute energies in gases, which means the entropy increases from solids to liquids and from liquids to gases, and vice versa, from gases to liquid, the entropy decreases, and from liquids to solid, it decreases again. Why is that? Because there is more disorder in gases, and there is much more ordered arrangement in solids. More the order, less will be the entropy, more the disorder, more would be the entropy. All right. Although the entropy is mentioned as the ways of a number of ways of energy in a system to be distributed, but it's also a very good idea for a student to understand it on the basis of order and disorder. The more the molecules are orderly arranged, lesser will be the entropy. The more the molecules are disorderly arranged, higher would be the entropy. Moving on, if the entropy of the system increases during a reaction, it is more likely for that reaction to occur. When dissolving ammonium nitrate in water, although the process is endothermic, but there is a point of entropy in here. The ammonium ions and nitrate ion particles in a giant lattice become separated from one another. They're not orderly arranged anymore. In fact, they get the freedom of movement in water. The disorder in the system has increased. Hence, the entropy of the system has increased, which outweighs the effect of enthalpy. And even when the reaction is endothermic, it is able to happen accordingly. So the driving force is not enthalpy itself. The driving force is actually entropy of the system, which is increasing. Another example is the reaction of baking soda and vinegar. This is an endothermic reaction. It occurs spontaneously. The reaction produces a gas which leads to the increase in entropy of a system. So this reaction is commonly used in science systems where the students like to make volcanoes, as you can see in the diagram. The student has made a volcano and he's going to put a mixture of baking soda and vinegar. Students usually put vinegar in the beakers, they color it out, and they usually put the baking soda inside the volcano first. As soon as they pour the vinegar on top, it produces a gas and everything comes out with a lot of effervescence and bubbling. So they're able to imitate the volcanoes. But in this case, to understand the chemistry, the entire driving force for the reaction to occur was increase in the entropy of the system. I hope that makes sense. And it also finishes the chapter.